one of the first systems that we're going to look at is this thing called a Lotka-Volterra equation, or a predator-prey system. And so first what I'm going to do is I'm going to explain the derivation of this, and then we're going to go ahead and use some technology to be able to solve one. And so a Lotka-Volterra equation has the form dy dx, or dx dt, excuse me, ax minus beta xy. And then a second equation in the system, dy dt, negative by plus gamma xy. And x is going to represent the population of the prey, and y is going to represent the population of the predators. All right, so this is our prey, and these are our preds. All right, and that's the change in the preys and the change in the predators. Okay, so dy and dx and dt, and then dy dt represent the prey and the predators. And so ax means that there's a proportional constant at which the population of the prey is going to grow. All right, and there's infinite food, so let's just assume that the predator or the prey will grow because they just have enough vegetation, etc. So this is a proportional constant. And this guy right here, this minus beta xy. Now, this is going to be represented by the interaction of the two species. All right, so if the predator and the prey meet, then the predators are going to kill the prey. And what's the likelihood that they meet? Well, that's going to be beta. All right, so that's basically going to be the rate of change of the prey. All right, so rate at which we're preyed upon. All right, and we know that some prey are pretty good at hiding and others are not so good. All right, so beta might be higher for something like a plant as opposed to something like a jackrabbit or something that's a little bit smaller and faster. Now, for the predators, by, this is going to be the rate at which the prey or the predators are going to decrease in the absence of the predator or the prey. All right, so this is going to be a proportional constant for which the predators are going to grow. And this gamma xy is the exact same thing as above, right? This is going to be the rate at which the prey or the predators are going to increase. All right, so rate of increase of the predators. All right. And so we end up with this Lotka-Volterra model. All right. And again, we're under the assumption that there's no other sort of factors that are going to try to influence the population of both of these. So given that, let's take a look at a couple example problems to where we can go through and perhaps just go, set up one of these Lotka-Volterra models and then go ahead and solve. All right, so suppose we have a population of rabbits and wolves. Rabbits are going to be the prey, wolves are the predators in an environment described by a Lotka-Volterra equation. We have A is going to be equal to 0.08 and beta is 0.001. B is going to be 0.02 and gamma is 0.00002. And T is going to be the number of months. So let's construct the system, find the equilibrium solutions. And then we're going to find an expression for dy dx. And then finally, we're going to find something called a phase plane, all right, or a phase plane, excuse me. And we're going to be able to describe what that looks like. Okay, so for part A, our differential, we have dx dt, and then we have dy dt. Right. And remember, our equation is ax, so 0.08x, and then that's basically saying how quickly the rabbits are going to increase, all right, minus beta, or 0.001xy. All right, so this is going to be the rate at which they decrease when the prey and the predators accidentally meet or intentionally meet. All right, so basically they get a hold of one of these rabbits and just goes by them. All right, now for the other system, or for the other equation, we're going to have minus b. All right, so that's going to be 0.02y. All right, so basically what we're saying is that in the absence of the predator or the prey, the predators are going to decrease, and then plus So this is going to be the rate of increase, 0.00002 xy. Now, that's our system, and we want to find these equilibrium solutions. Now, equilibrium solutions are when the derivatives or the rates of change are equal to 0. So that's going to be dx dt is equal to dy dt is going to be equal to 0. All right? And so all we're going to do is just set the above systems to 0. So we have 0 and 0. It's going to be equal to 0.08x minus 0.001xy, and then negative 0.02y plus 0.402xy. Right? And how do we solve this system? Well, what we can do is we could just go ahead and factor in x from the numerator, or from, excuse me, the top equation, and then from the second equation, we can factor out a y. Right? So that's going to be 0 and 0. And if we factor out an x and we factor out a y respectively, we're going to get 0.08 minus 0.001y, and then negative 0.02 plus 0.00002x. Right? Now, all we have to do is just set each of these equal to 0. All right. Now, one solution, excuse me, is very apparent. Okay. So right here, this just tells us that x is equal to 0 and y is equal to 0. And that certainly makes sense. If there are 0 rabbits and there are 0 wolves, there is 0 change in the wolves and the rabbits. All right. So that's actually the trivial solution. It makes sense, but it's not really helpful to us. The solutions that are helpful are going to be these guys right here. And so we're just going to take 0.08 and set that equal to 0.001y, and we're just going to divide both sides by 0.001, and that's going to imply that y is going to be equal to 80. And for the other equation, we're just going to set 0.00002x equal to 0.02, and this is going to imply that x is equal to 1,000. And so what does this mean? Well, this means that equilibrium of the system occurs at 1,000 rabbits and 80 wolves. Okay, so that'll be enough to sustain the system. All right, so that means that the rabbits can still reproduce by grazing, and the wolves can still survive by hunting the rabbits. Right. So, and also that's true, and we should also state that also true when neither animal is present in the system. All right, but that's fairly trivial. All right, but this is the one that we really want. Okay. And so the question is, what does that mean to us? Okay, so I mean, we can figure out the equilibrium solutions, but what more can we deduce from that? So in the next video, what we're going to do is we're going to find an expression for dy dx if we're going to interpret it, and then I'm going to show you how to produce a phase plane and what the key characteristics of that phase plane are going to be.